greater than 2, or you have ti plus 1, ti equal to ti plus 1, ti. Okay, for the other of time.
Can I ask a question? I forgot. I know this, but I forgot. So it is the same as the permutation, except that you don't have the square equal 1.
Yes.
Always. For all these groups, right? Okay.
This group acts on the quantum group by automorphism which are denoted by the same letter ti. So you have formulas for ti. I don't want to write them, but it's inside the Jean-Presley book and inside the article. So you can define ti automorphism of the quantum group, which satisfies the same relations.
So you give them on generators?
Yes, you can.
No, the definition is on the generator.
Yes. So you do formulas.
No.
Yes.
Yes.
Yes. All is inside the article. It's not interesting.
This action, when Q is equal to 1, what is it?
I don't know. It's
You don't know.
I think you can. It's not easy to define. Perhaps. I don't know.
No, I wonder.
But yes, you have also an action of EG by G. Yes.
Yeah, I was wondering what the action was, but
So
the formulas are complicated. You cannot look at them and tell.
yes. No.
Ah. So we will give them on the xj and then we will give them on the k's, right?
Yes.
Both.
Yes.
Okay.
It's completely defined on the generators of the quantum.
And on the
So,
L.
when you do that, after you can obtain one vector on this vector space.
It's probably it's compatible with the action of the variable on the spaces.
Yes.
I wonder that
Yes.
this.
Do you think that Giovanni last week gave an idea of the definition of
Yes.
this action? It is defined in terms of the action of the variable on the roots, on the second.
Yes.
But it doesn't project an action on the variable in the quantum case. There's no action on the variable.
No.
So you have to fix the adjusted expression.
Sì, è vero.
So we have the longest element in the variable, and we fix adjusted expression of this element.
Interessante quella classica, perché c'è una cosa assolutamente nuova di questa che c'è.
Okay, so if you do that, you can obtain all the all the rules in this way. So, in this way, B1 is equal to alpha A1 so this is simple rules. B2 is equal to SI1 alpha I2 and we continue this process. SI1 SIN-1 alpha N. Okay, and if you do that, you take all the root vectors. Okay. And here we will do the same things with these operators. Spirit, we define the root vectors. Where x so x1 plus and minus is equal to xa1 plus and minus. x2 plus and minus is equal to ta1 of xa2 plus and minus. Yes, okay. I mean,
you can't call them exercise, right? You have to call them something else. Right, better.
So with these elements, we will be able to define a basis of the contour group as vector spaces, as vector space.
So we change basis.
Sorry?
So the x beta k will change the generators? No, or the basis has vector space for UQG. What is changing? I don't understand.
So you have you have the xi plus and minus, but it generates the contour group as algebra.
Sure.
And you want a basis as a vector space, and you need these objects, and they will be
You want the analog, the quantitative
it's a quadratic theorem for.
Well, if you do quantitative profit with what you have, I mean, you don't need to go through this, right? For the PBW.
You need.
No.
If you look at the quadratic profit
Right.
theorem for G, you need all the vectors.
No. What I'm trying to say, yes. What I'm trying to say is that in the quantum group case, you don't really have to go through these T's to give you just a basis as vector space for UPG, do you?
You need to have a good basis, yes.
You?
To have a good basis of the...
No, good basis, but for just having a basis, you don't need to go through this, right?
How do we define the root vectors? This is the way you define the root vectors for UPG.
But for the PBW, you don't need the root vectors, you just need vectors, right? Why do you need root vectors?
No, you need them all. You need the root vectors.
Yes, with the root
No.
vectors, yes.
No, I see.
For UG, yes.
You need all of them, this is why. You are just the generators and you want all of them,
Yes.
that is the point, okay. I see.
Yeah, it's okay.
I think,
For G, you have
second
the
problem.
generator xi plus minus hi. Yes, if you go to UG, you have the programmable factorial, but you need all the x alpha plus and minus hi with alpha and delta plus. So you have to order them, like here. Perhaps I can write beta I. And for UG, so the basis is obtained by monomials in this determinant. So we will have the same things for the quantum group. Okay, so we have the root vectors. We can define UQ n plus, which is generated by X. This is a subalgebra generated by these generators. UQ n minus same. And UQ h.
I leave a question from before. It just occurred to me that we don't have quantum cell. Do we have quantum cell?
Quantum cell relations?
What
Yes.
are they?
Um,
You didn't write.
no, because it's quite complicated and no interest. There is no interest for this talk.
So but the quantum cell
Yes.
must be in the set of the you know, when you write a UQG,
Yes.
quantum cell will be there.
Yes.
Sure. Oh, you didn't
Yes.
say it, so
No,
maybe.
he said, I'm not going to write them.
Maybe, okay.
But the quantum group of n plus,
Yes.
it's this by definition, because in the original definition,
So
you can consider the quantum group of the algebra which is not simple.
Mm.
So the symbol UQ of n plus is
Is a definition here.
this is
Yes,
the
this
definition,
is the subalgebra generated.
just the subalgebra.
But if you want a presentation of this algebra, it's just generic.
No, you cannot give you cannot define UQ of a generic Lie algebra. Or
No, it's you can define
semi-simple Lie algebra.
also for Kasumi algebra.
Okay.
But you are also using the term of quantum groups where you should give data and antipode and everything, right? And you're not doing it, but you
No,
should.
yes, but we
No.
don't use the algebra structure. So.
Yeah.
Yes, there is a algebra structure on the UQG, but it's not interesting.
No, because this I think comes towards the answer to him, because if you just define the formation, you can do whatever you want. But if you are asking, I want something that is antipode, that it has, then your choice is much more restricted. That you see what I mean? I mean, you don't just want an object that on Q is equal to 1 goes to that one, because this is too simple, I can do whatever I want. But I want something more than that.
Is it simple? Okay, but does it exist a definition of the quantum loop of the algebra, or just the simple?
Yeah, yes, there is. It's not the giving. It's you take an off algebra with a parameter. When the parameter is suitable, spatialized, you get the algebra you're starting from. This is a more right. Very general.
According to the definition we are giving of, this is what is usually called the quantized development.
Yes,
algebra.
yes,
And
yes.
this is the definition we give for every simple Lie algebra. So I think that Fabrizio is saying, now when you write UQ of M plus, you are giving a definition of this object, because M plus is not a simple
No.
object. And indeed, he is giving a definition. So let's say
Yes.
we are denoting by UQ M plus
So
It's
it's
about-
the
yes.
subalgebra
Yes.
generated by.
Yes, but it is miracle that the entire antipode they will restrict to this, right?
Yes.
They do restrict.
Yes.
Yes, it's not
Then we can
so.
study this object from the point of view of algebras, but I think this is not the purpose of, this is not the point of view of.
It's not
I
using
guess.
of the structure anywhere. This is very surprising. No?
It appears in one.
It appears. It must appear. When it deals with the group, tell me, that is what
Yes.
is yes, because it's the dual. The delta is the dual of the multiplication. If you want to do anything, you need
To say that it's Poisson.
of course, yes.
I
How
will
do
not
you-
give it.
We wait.
Yes. So yes, you can define a quantum group for a simple algebra. You can define for quantum algebras in general, but I don't know if you can. I've never seen that for the algebra.
Yeah, I think this is a definition, that's enough.
Yeah.
And they always pronounce to be off algebras.
Sorry.
They're always off algebras.
Yes. Yes.
Quantum group, the definition of quantum groups requires it is alpha.
Yes, this is why they are called groups.
Yes. They're not groups though, right? They're not groups in
No.
any way.
Yeah,
No, I think the
Yeah.
word groups comes from.
So the quantum group.
No, because it's the formation of an
yes.
object linked to a group.
But when we define the quantized development algebra we are defining, we don't require anything else than what is said.
No, of course.
And then this happens to be enough.
But it's true that there is a link between the algebra structure and the term of quantum group. It's come from this.
Più grande di questo evento e lo faccio dopo.
No, ma la domanda è assolutamente giusta, cioè sono sempre no, la risposta è sì. No, non è che tu lo chiedi nella definizione che lo sì.
In questa definizione.
Esatto, nella definizione è questo.
La nostra, perché tutte le altre sì, lo richiedi. Cioè, la nostra perché è automatico, perché c'è
Esatto,
dentro,
è una
però...
cosa che segue dalla definizione.
So now using these multipliers, we can construct a basis of UQG, and for that we will define So for a set of integer like that, we will define the monomial x plus r is equal to x beta 1 plus r1 x beta n plus r. We do the same with the minus. And I have to define this for its mean x have a plus and minus for the notation. It's equal to x plus and minus square k, and we divide by factorial of q, but like quantum numbers. So k q is equal to q power k minus q power minus k. Note that if you, so we said that it's a quantum integral, and if you take q equal to 1 inside this relation, you obtain k. Okay? So factorial is just just this product. And for every sequence of integral. So here it's a positive integral, and here just integral. Because it's more polynomials of parameter L1 plus 1 and N S. Okay, and now so this is the W theorem. Multiplication times isomorphism of vector spaces between UQ minus UQ H S This is the first part. It's called the triangular decomposition. The negative part, carton part, carton en second genre, and the positive part, and the basis. This product form a basis of the positive and the negative parts.
But since you are considering coefficients in CQ, why did you need to multiply this various elements by KQ factorial? This is not needed for.
I think it's useful for
It will be useful
for after, yes. No, Q is a formal parameter, and we specialize Q.
Yes, but if you consider x alpha plus to the k,
Yes.
just without
Yes,
considering
it
this,
was.
you
Yes.
obtain also.
Just a normalization, yes.
Yes. Another question: if you don't consider an order of the reflections which are of the roots, which is constructed in that way, you don't obtain a basis.
Sorry?
So this basis depends on the order you chose of
Yes.
the roots.
Yeah.
If you consider another order, you don't obtain a basis.
Si, si.
You get another basis.
Yes. Another basis, but with other.
So if you choose an order which is not constructed in that way, you reduce the composition.
No,
Because you know, in the standard case, you may take any order of the roots. You
Yes.
don't need to choose a convex
But
order.
at the beginning, we fix an expression of a reduced expression.
Yes, and then an ordering of
Yes.
the
It
roots.
depends of this reduced expression. For any reduced expression, you obtain a.
Yes. So my question is, if you choose
arbitrary.
arbitrary an order of the
But you
the
don't
roots.
know how to define the root
Right.
vectors,
No, so
because the definition of the root vectors,
Uh-huh.
Yes.
exactly,
Yes,
the
it's
contraction
right.
of the root, sorry.
Yeah. No, you have the
Yes.
If you want to obtain all the root vectors, you have to do that because I think if you want
Oh, yes.
you choose an ordering, you can obtain 2 times the same vector.
So I go to another question. You're taking this from the friend S, right? No, this is taken from where? This that you're describing right now, this basis.
Right?
Where is it? Where is the source for this?
You can so it's
It's
explained
not in the
very
paper.
explained inside the paper, but very quickly. And
In
you
the
can
paper,
find- yes.
because I'm surprised that the factorial comes for the x and doesn't come for the L. This is strange. Are you sure? I'm just L is taken like that.
No, it's always
It's not
like that.
taken the coefficient binomial coefficient coming in no.
In fact, these elements appear inside the quantum set relations, and in the relations defining the quantum group, you just add this product.
No, it's a question. So really, in the PBW theorem that he analyzes, this L comes as
Yes.
L. When you specialize to get to the H, it's not a binomial coefficient there. I'm surprised. There is analogy with the constant integral form, right? Very strong analogy. The root vector is divided by the factorial, but the Cartan, do you know the constant integral form? No. The factorial, it looks the same, but the H elements will come with binomial coefficient. So I'm surprised.
They do the same.
Huh?
Yes,
Okay. A different
yes,
purpose.
it's the same inside the article and inside the
No, I'm surprised by this analogy that doesn't go to the Cartan, but okay, they may have different values and they don't need it.
So now, from now, Q is an indeterminate, and we want to specialize Q to a complex number, non-zero complex number. And that's why we work with UQG and not with UHG, you know. We, at the beginning, I talked about this algebra. This is a deformation of UG. And we choose this solution because now we can specialize Q in one value. In this context, you can't because this is a formal power series in H, and the only value you can take for H is 0. with this algebra, you can specialize Q at any very complex number. And for that, we have to. So it's called non-restricted specialization. So you want to give a value for Q, but you have to go in an algebra. Yes, you can't do that in a UQG directly because you have, for example, if you take Q equal to -1, you have inside this relation, you see, that's okay, so you have to take care when you specialize Q, and to do that.
In this case, it's just the sum 1 plus Q plus Q squared plus Q to the given plus so it's not a problem if you put Q.
Yes, it's true. Yes, it's true. So, to do that, we denote H, J. So, A.
There is one thing I still don't understand. Can I ask?
Yes.
Ah, exactly. This is the question. That question you answered.
Yes.
Because I was like, you insisted to have the algebra over a field, but over a field there is a problem if you specialize. You have
Yes.
to go to a ring, but now you write the ring, so it's no problem.
Yes, so for yes, you can't work
You cannot.
directly on this field, and you want to specialize, so you have to go in this field and in this field, in this ring. Sorry, you can specialize Q at any value. You don't have problem. If you do that here, you want to specialize Q at A, for example, and there is this fraction inside this field, and you can do that. So we will consider this ring, and we will consider the sub-algebra of UQG. So this is how we do for when you have this sort of problem. We consider a ring where you can specialize Q at the value you want, and after you consider the subalgebra generated by some elements you are interested in. Now here we do a choice. You can choose other specialization of UQG. Here, this is the specialization of the continuity processing. But there is another specialization which is interesting. So, okay, you do that?
So maybe that's why you chose that basis.
Yes.
This is still a basis.
Stava su per fare una difficile specializzazione, no? Perché le basi sono difficili da trovare. Se tu usi in particolare che tutto vada bene, non ci sono cose. C'è molto origine in questo studio. È molto misterioso.
obtain something which is called integral form, and the meaning is UQG. Okay, it means a subalgebra such that you have natural map from this integral form you can extend the scalars to C. Okay. Yes. And you want that this map is a proper field.
So you have to check that when you multiply these objects, you don't get out.
Yes.
I don't see these allies really alone. These allies, how?
But for the Li,
I'm back with the binomial coefficient, because when you're doing the same for the constant integral form, this denominator, which is a factorial, is very important, because when you bracket two things that lie like Cartan, this will come, and there it doesn't. I don't see. I will make the calculation because I want to check it. You didn't check that, of course. Who claims this? Cherry Presley?
Cherry Presley.
Cherry Presley does it, or he does it.
Both, but they just claim it.
Huh? They just claim it. Ah, such an easy calculation. Scusa, dovevano finire. No? Cioè, è naturale che quelli rompono. E io qui non ci sono, perché non ci sono. C'è sempre x 3 diviso 3 fattoriale.
So you add this subalgebra over this ring, and you want that when you extend the scalar this at the beginning, this map is a morphism. And it's important because with this hypothesis you are sure that you don't lose something inside this algebra.
Forse capito. Ah, è andato a lavorare.
Okay.
No, me too, I have to go in a while.
So now, from this point we can. Sorry.
No, it is. I don't know what time it is. What time is it?
4.
It's 4.
Yeah, it should conclude in a few minutes.
Conclude,
Okay. Yeah. Okay. Good. Just explain. I just did this
Hai fatto lo stesso? Se tipo va a finire.
No, if you take LCR, a non-zero complex number, you can specialize the norm has to tell specialization.
Certo, potrebbe essere la stessa.
Denoted by UFCM G and UQG is the C algebra. So I have to explain how C is a value, but it's obvious. you obtain if you assume you have epsilon 2di different to 1. So it's this possibility is to make sense for 1 over epsilon di minus epsilon minus di. You have these fractions inside of the, so you have to assume that. And if you do that, u epsilon g is C algebra generated by the Li plus or minus 1 xi plus or minus with I equal to 1 to n, and and the relation between UQG is Q equal to epsilon. Okay, so to define U epsilon G, you take the relations which define this algebra and you take epsilon equal to Q inside these relations. So all of these things in integral form is to obtain that. Yes. I can stop here.
Che bravo, sei in quel...
Un po' più di
meglio nella volta. No, ha spiegato tutto, no?
Bravo. Adesso devo offrire una cosa da bere.
Sì, davvero. We must be forgiven. You missed the part.
Oh, yes.
Because I forgot, so I looked for you at 1 minute.
Yes,
10 minutes to 1, but you were not here. I went to your office. You were out for lunch. Vabbè, che ricevuto.
Bene, bene. Ciao ragazzi.
Giovedì prossimo alle 2. Ok. Oggi alle 2:30 visto la...
Ah,